determining enthalpies of reaction from standard enthalpies of formation. In this video, we are going to define an important term called enthalpy of formation. Because this changes based on the conditions, we also need to define a standard state, and we'll discuss that in this video as well. Standard state is used to calculate the standard enthalpy of formation. For a gas, we're talking about a pure gas at 1 atm. For a liquid or a solid, a pure substance in its stable form at 1 atmosphere in the temperature of interest. We're normally going to do this at 25 degrees Celsius. It's what the tables are done at. And then for any aqueous substance, standard state is going to be defined as exactly 1 molar. Now notice this doesn't say 1.0 molar, it's 1.0 to infinite numbers of zeros molar. The standard enthalpy change is going to be the change of enthalpy for a process when all of the reactants and products are in their standard states. Now these are values that you can look up on tables. You may notice that on a lot of these values, you're going to see a little degree sign up in the upper right above the statement. You'll see this for delta H. When we get there, you'll see it for delta S. And when we get there, you'll see it for delta G. This little degree symbol is just defining your standard state. Now the standard enthalpy of formation, which is also called the standard heat of formation, is the change in enthalpy when 1 mole of a compound is formed. Now, the important part is formed from its elements at standard state. So remember what we talked about with standard state. 1 atmosphere, 25 degrees Celsius, and or 1 molar, depending on the phase that you're talking about. Now, a pure element in its standard state, so let's say copper in its standard state, is going to have a enthalpy of formation of 0. Any of the diatomic gases, so H2, F2, Cl2, Br2, are going to have a standard formation of 0 in their diatomic. Something like sodium, a typical metal, is going to have a standard enthalpy of 0 in its standard state. This is something you have to know. I wouldn't give this to you and it wouldn't be listed in a table. For anything more complicated than something in its standard state, you're going to look this up in the back of a book or the internet. Let's do an example with this. Now, here I picked an example that you might know from your biology classes. I picked photosynthesis. So in photosynthesis, we have carbon dioxide and water going to sugar and oxygen. Now, the first thing you always do when looking at a reaction, and you might get lazy about doing this sometimes when we get further into the class because you think, oh, they always give me equations that are balanced. So I didn't this time on purpose, so that you had to think about it. So balance this reaction before moving on. So now we have our balanced reaction. If you need some extra help in learning how to balance, go back to the introductory videos on how to balance reactions. Notice off to the side I have a table for you. These have all the standard enthalpies of formation. You're going to use these to solve for the enthalpy of reaction. If you take up all of your values in your products and you subtract all of your values in your reactants, you'll get your delta H. So the equation for this, which don't let all of the symbols here make you nervous, is just that you sum up all of the products and you subtract off the sum of the reactants. Products minus reactants. Take a second before moving on and see if you can do this yourself. So when we go up to add everything up, we look at our products. We have 1 glucose, that's C6H12O6. So we have 1 of those, and then we add in our 6 oxygens. And you might be saying, but you didn't give us the H of oxygen. Remember what I said about an element in its standard state. Oxygen's a diatomic gas. It's in its standard state, it's going to be 0. So that's why I wrote in the 6 times 0. Of course, you wouldn't need to write that in, but it's my reminder to you that it's equal to 0. Now you subtract off your reactants. So we have 6 carbon dioxides and 6 waters. So each of those get subtracted off. And we come up with our final value. So we have 2,802 kilojoules. Now let's check this out and make sure that our sign makes sense. Because anytime you do one of these reactions where you have a feel for whether it is endothermic or exothermic, and you have a feel for whether it is absorbing energy or releasing energy, you want to make sure the sign makes sense. This is photosynthesis. So we know that it's taking in energy from the sun to make this happen. So we know that it's going to be an endothermic reaction. We would expect then that it's positive, and it is. So that tells us that it's likely we didn't make some sort of silly mistake that messed up our sign. Now to quickly review everything that we did here, we found our delta H of reaction by comparing our delta F of our products and reactants. Delta H of formation is always going to be 0 for an element in its standard state. For anything else, you would look it up on a table. Because this is simply the enthalpy it takes to make a species with its component elements, not something you would be expected to memorize. Now, things to just remember and be careful of. Anything in its standard state equals 0. Now, the tricky part on this one is remembering that your diatomics are equal to 0 too. So H2, N2, O2, F2, Cl2, Br2, and I2 are all going to be 0 as well. All the elements are just the element on its own in its standard phase. Also, be very careful when you go to the back of the book to make sure that you're looking up the right phase. Many of these species will have 3 things listed, and if you pull a solid when your reaction has a liquid in it, you're going to get the wrong answer. So those are just some kind of problem-solving help as you're going through your problems.